Welcome! This is the first video in a series that is going to introduce the complex numbers step by step, very carefully and slowly with lots of explanations and worked examples. Before we introduce the complex numbers, we start by giving a review over the well-known number systems. So we start with the natural numbers 1, 2, 3, 4 and so on. And here we list one of the problems that exist in the respective number systems. And the problem here is that a simple equation like this, x plus 2 equals 1, has no solution in the natural numbers because the solution would be minus 1, which does not exist here. So this leads to the integers. We take all the negative numbers and the 0 and obtain the integers. So we go also infinitely long in the negative direction. But here we have another problem. A simple equation like 2x equals 1 has no solution in the integers because the solution would be 1/2, which is a fraction which does not belong to the integers. So to obtain solutions of equations like these, we construct the rational numbers, which is the set of all fractions. I always mess up the numerator. I think the numerator here is any integer and the denominator is a natural number. So all fractions build the rational numbers. And to depict them, I draw a squiggly, a dotted line, because there are lots of rational numbers, but there are points missing here. For example, if I construct a square of side length 1, take its diagonal, then this is clearly a constructible length. Now I project it down on this line, and here is no rational number that belongs to the length of this diagonal. So, written as an equation, I can say the simple equation x squared equals 2 doesn't have a solution in the rational numbers because its solution would be square root of 2 or minus square root of 2, and it's a well-known fact that this is an irrational number. I cannot write it as a fraction. So finally, to solve this problem, we construct the real numbers. And now, missing a better definition in school, I just tell you the real numbers are any numbers that have a decimal expansion or can be written as a decimal number. Constructing the real numbers is a whole different project. So we're going to use this mediocre definition. For example, 0.1 is a decimal number, which could be written as 1/10. So this is actually a rational number. 0.1 period, no, that sounds wrong. So words are failing me. 0.111111, infinitely many ones. I don't know the English term. This could also be written as a rational number, 1/9. But then there's also stuff like square root of 2, which has 1.41 and so on, a decimal expansion that never gets periodic and never stops. And these are the irrational numbers. And if I take the rational numbers and the irrational numbers together, I get the real numbers, which can be depicted as this smooth line where no points are missing. So to do calculus, this is pretty good setting because I can do all the algebraic operations and there are no points missing, and one can show that limits always exist. Like every Cauchy sequence in the real numbers has a limit, but therefore doing algebra there's a fundamental problem. This simple equation x squared equals minus 1 obviously has no solutions over the real numbers because any real number squared is either 0 or positive. So, from an algebraic point of view, we can't stop here. And this step takes us into the world of the complex numbers. Formally, I could write the solutions as plus minus the square root of -1, which obviously does not exist in the real numbers. And in some books, you're going to read that this is the definition of a new number called the imaginary unit, and from then on we calculate with this number. This, of course, is a completely nonsensical definition, because I cannot just define something that clearly doesn't exist in my known number systems. So we're going to take a different approach. We use the approach that Sir William Hamilton used in 1835. Complex numbers had been around for about 3 centuries before Hamilton gave them a clear setting with no mystical expressions like square root of -1. So the motivation for this definition here is the following. Here on this real axis, there is no number that satisfies this equation, no number that squared gives you -1. So what could we do? We just add another axis. This axis is called the imaginary axis, but we're going to see there's nothing imaginary about it. The reasons for this name will become clear later on. So as a set, the complex numbers is nothing but the real plane, R2. So the set of all vectors AB with real components, nothing else. So this here is a complex number, usually denoted by small z, just a vector with 2 real components, A and B. Now, Hamilton's genius was to introduce 2 operations on this set. The one has been long known, it's simply vector addition. So we add 2 complex numbers, which, remember, are nothing but 2-dimensional real vectors, in this way. For the moment, I use this notation plus with the circle around. We're going to drop that notation soon. So how do I add 2 complex numbers? Well, I simply add their components. So this is the well-known law of vector addition. Simply adding the components in the real numbers. This is nothing new. The new part comes here. Hamilton was able to define a multiplication. So I can take 2 vectors, 2 complex numbers, and multiply them so that the usual rules for multiplication hold by this strange definition. Hamilton says AB times ZD is defined as follows. For the first component, we take A times Z in the real numbers minus B times D, also in the real numbers. For the second component, we take kind of a cross product, A times D plus B times Z. When you see this definition for the first time, of course, it looks very strange. And it's not clear how anybody should think of this, but we're going to see shortly that this is a very natural way to define this multiplication. So we start by familiarizing ourselves with these 2 operations. So given our 2 complex numbers, Z is the vector 1, 1, which you see here, and W is the vector 0, 2, which you see here. And now you should stop the video and familiarize yourself with these 2 definitions and simply compute Z plus W and Z times W. Please do that. Okay, by now you should have found out that the sum is the vector 1, 3. If you look here, this can be interpreted geometrically very easily because we have the well-known parallelogram rule. So I take these 2 vectors and add them by the parallelogram rule. So this vector is the diagonal in the parallelogram that is spanned by Z and W. The product of these 2 vectors or complex numbers is -2, 2. So here we have the product. Here it's not that obvious what the geometrical interpretation might be. We're going to address that later. Maybe you already have an idea. Now here's an interesting fact. If you take v squared, which means multiply v by itself, you end up with, please check this or do it yourself, -4, 0. So a vector that lies on the negative real axis. So something squared might be interpreted as negative in some sense. That is very interesting, because this is exactly what we're looking for, right? So a very important observation is that R, the real numbers, are contained in the complex numbers. As a set, this is clear because clearly the real axis here is contained in R2 in the complex numbers. But also, if I take the addition, the sum of two vectors looking like this with second component 0, so lying on this axis, and if I take the product of two such vectors, the following happens. Clearly, the sum is simply a plus z, and here we have 0. So it's as if I were adding real numbers on the real line. This is not surprising if you think about the geometric interpretation. Now for the multiplication, we have a times z minus 0 times 0, and then we have a times 0 plus z times 0, which remains 0. So also the product of these two vectors is nothing but taking the product of the two real numbers, a and c, the first component. And in this sense, the real numbers as a number system with addition and multiplication are contained in the complex numbers. So the complex numbers are an extension of the field of real numbers. If you're a fan of abstract algebra, you could also say this in the following way. The map iota, small iota, from R to the complex numbers, which simply maps a number to this vector. So we take this number and identify it with the vector a0. This is an embedding of the real numbers into the complex numbers, sometimes written with a crooked arrow like that, which means iota is a one-to-one map, which is obvious, and iota fulfills the following two conditions. Abstractly speaking, it's a ring homomorphism. It doesn't matter if I add the numbers a and z first and then map it, or if I map them first and then add them in the complex numbers. Same for the multiplication. Doesn't matter if I first multiply a and z and then map them with iota, or if I map them first and then take the product in C of the images. These conditions are simply these two calculations that we just did. So if you didn't understand that, do not worry. So if we take the number 1 and map it to the complex numbers using this iota, or simply saying 1, 0 is going to be defined as the 1 in the complex numbers, then it's easily seen that this is the multiplicative neutral element. Meaning, if I take any complex number times this element, then the number z won't change, and the same from the left side. So let's check this. AB times 1, 0. If you want to, please pause the video and try to calculate that on your own. Okay, and you will obtain, this is a minus 0, and here b times 1 plus a times 0, so just ab. So z doesn't change, and the same from the other side. So this here is the neutral element of the multiplication. And now comes the most important definition. The single most important complex number is represented by this arrow pointing straight upwards with a length of 1. So simply the vector 0, 1. Euler, the great Leonhard Euler, called this the imaginary unit for reasons that shall become clear shortly. But we see, using Hamilton's definition, that there's nothing imaginary or mystical or magical about this at all. This is simply this vector of length 1 pointing straight upwards. Now the most important property of this number is that if I square it, I get minus this element, minus 1. So in this sense is the equation, this was our starting point. Here, the equation z squared equals minus 1, meaning minus this vector, has solutions in the complex numbers. Okay, one of the solutions is simply this imaginary unit, because if I take I squared, which means I times I have to multiply these two vectors using this rule, and I would not want to deprive you of the joy of doing this on your own, so please pause the video and do that, or do it in your head, and you will find 0 minus 1 times 1 is minus 1, and here 0 plus 0. So this is minus 1, 0, which is the same as the negative vector 1, 0, which is negative 1 in the complex numbers. So I is the solution of this equation. And if you're bored, you could do the same calculation for minus I, which is 0 minus 1. This will also give you minus 1. So this equation has at least two solutions in the complex numbers. So, to conclude this introduction, in this sense you could say that I is actually the square root of minus 1, because if I square it, I get minus 1. But we're going to wait a long time before we do this, because this only leads to confusion, as in the 300 years before Hamilton. But this here explains the name imaginary unit, because when people started using this quantity, they thought it had to be imagined because it clearly didn't exist. The square root of minus 1 is nothing real, it's no real number. And this term stuck till today. But you should have learned that nowadays there's nothing imaginary or mystical or magical about this number or about the whole complex number system. Complex numbers are simply vectors with real entries using these two definitions. And in the next video we're going to see why this isn't as magical as it looks and what motivated Hamilton to give this definition. Okay, I hope that was an enjoyable and understandable first introduction to the complex numbers. Please stay tuned, a lot more videos are to come. See you soon.